Okay, so how is everyone doing? Doing well? Yeah? You can say doing well on while you are being recorded. Okay. Alright. Okay, so let's start. So this week, and maybe another 1 week or two, I don't know, is basically going to be about the theory of tight cuts. Sometimes I call it the tight cut decomposition theory, same thing. Right, so let's do a quick recap of basic things that has nothing to do with matching covered graphs. Given a graph and a cut, right? We all know what a cut is. A cut has two shores, the x and its complement x bar. Typically when I write x bar, I mean the vertex set of the graph being considered minus the set x. And of course, if there are multiple graphs, then you have to specify what the bar is with respect to. Okay, so for a cut partial x of a graph G, you can define these two graphs where you shrink the shore into a single vertex and you don't throw away parallel edges. Right, so those two graphs, we will call them the cut contractions. So the cut contractions with respect to a cut partial x are the graph G shrink x to a single vertex and G shrink x bar to a single vertex. Here I have drawn them. This is G shrink x. If we want the notation for the smaller vertex, we will use this. If I don't care about the symbol, I will just write this. Similarly for the other shore. Right? Here's a concrete example. This is clearly not a matching covered graph. It is odd number of vertices. Here is my cut partial of x, and here are the two contractions. Did I draw them correctly or did I mess up the drawing? Drawing is okay, right? Observe that the original graph was simple, but the contractions have parallel edges in this example, right? Okay. Alright, and before we go into tight cuts, which we already defined, let us quickly recall separating cuts. So a cut is a separating cut for a matching covered graph, of course, if both contractions are matching covered. Yeah. This is a cut of a matching covered graph whose both contractions are also matching covered. Maybe I should say whose both cut contractions, do not confuse with the usual contraction in a graph. Okay, so any cut for which both cut contractions are matching covered is called a separating cut, and perhaps the most standard example of a separating cut is this one. Right here you can see that of course every trivial cut is separating. Observe that every trivial cut is a separating cut. But what is more interesting is a non-trivial separating cut. So here is a non-trivial separating cut in this graph. Okay, good. And we observed last time that separating cuts are essentially the converse of splicing two matching covered graphs. In the concrete sense that if you splice two matching covered graphs, then you will get a matching covered graph, right? That's an easy exercise. And the resulting splicing cut is naturally a separating cut. Its two contractions are the original two graphs you spliced. Okay, so separating cuts may be thought of as a converse, or if you like inverse, I don't know, maybe inverse of splicing matching covered graphs, right? Okay, and I had given a TIY which was to characterize separating cuts. So let's look at that characterization. One more exercise. This is proposition 4.1 in Bondi and Lucchesi and Murthy, not Bondi and Murthy. Every separating cut is a bond. Prove that every separating cut is a bond. So both the shores should induce connected subgraphs, right? That's what a bond is. Good, so that's easy. That is a DIY. I think I'd given earlier the same DIY for tight cuts, but this is more general because separating cuts are more general. And here is another, maybe I'll write this separately. Okay. Let's look at a characterization of separating cuts. That is actually quite easy to prove. So I'm again going to leave it as a DIY. A cut C of a matching covered graph G is a separating cut if and only if. Last time this was a TIY because I did not even give you the statement. Today we will reveal the statement and make it a DIY. So, anybody? Any ideas about what the statement is? Assuming you have not seen this before 100 times.
One thing I want to say
yes.
that proposition 4.1 take a graph, I think take K4 and remove two edges, that one and that one.
Yeah.
And that is going to be a separating
So you are taking K4.
Remove two edges.
Which? Just these two?
Place this one and this one also.
Okay.
And remove two, these two.
Which two? Those two.
Rectangle edges, opposite. Yeah. Yes.
Okay.
Yes, now cut. This is a separating cut.
You think about it. You tell me. What are the two contractions? How many vertices does the contraction have?
Two.
No. Contraction is not two vertices. You have to take the shore, the cut contractions. By cut contractions, I mean this. You have to take the shore and make it a single vertex. So how many vertices will you get?
That is not a kind of edge contraction.
No. This is not edge contraction. Sorry. Yeah. So we are using the word contraction, but technically what we mean is cut contraction. Yeah. So cut contraction just means take the shore and make it a single vertex, like I did here. Yeah. So like this.
Vertex identification.
You can call it that, but yeah, we will use the word cut contractions. So the point is, one reason to use the word cut contractions is almost always when we do this operation, the shore will be connected subgraph. So because it is a connected subgraph, if you contract all the edges of that shore, you will actually get this graph. You can simulate cut contraction by contracting all the edges that are in that shore. And we will almost always use this operation when the shore is a connected subgraph. If the shore is not connected, then almost surely we will not even use this concept. So that is the reason we call it a cut contraction, but it is different from edge contraction. Yeah. So is this a separating cut?
No, it's
Not. Okay. Good. Yeah. Yeah, but it's basically what you said. Take all the vertices, identify into single vertex, and delete all the loops, which I won't say because anyways all graphs are loopless in this course. So therefore you have to by default delete loops. Yeah. Okay. Good. So now let's come back to this statement. A cut C of a matching covered graph is a separating cut if and only if something holds. And what we want is something similar to tight cut definition, but it's of course not going to be the same. So let's recall what a tight cut is. A cut C is a tight cut in a matching covered graph G if the intersection with every perfect matching is exactly 1. So this is the definition of tight cuts, and what I want is something that is vaguely similar to this but quite different in spirit actually, I mean in the details. Yeah. So you were close, you sent me a WhatsApp message. Okay, anybody else wants to give it a shot? If you have not seen this before, I think. So how do we characterize the separating cut? Maybe you can tell me what you had, Manoj.
For each edge in the cut.
For each edge in the cut, okay, let's write it. For each edge in the cut, there exists a perfect matching. M such that M intersection C is equal to 1. Yeah, this is what you want. Okay, this is an attempt. Does this work?
And does it mean E belongs to M? Do you mean that E is?
You want E to be in the perfect matching, right? Otherwise it's meaningless, right? Good. Such that, let's first write that, such that E belongs to M and M intersection C is equal to 1. Okay? So for every edge in the cut, there is a perfect matching of the graph such that it contains the edge and it meets the cut in exactly one edge. Well, what does that mean? That this is equivalent to something, right? If it contains the edge and its intersection is exactly 1, then what is the intersection? Then the intersection is E only. This is actually equivalent to M intersection C is equal to E. Yeah? So what does everybody think? Is this correct? Well, if it is correct, you have to prove the two sides. And if it is not correct, then well, you get stuck in the proof. But more interesting would be to get a counter example. Can you find an example where if this is not correct, then what you want is, you want this statement to be true and this to not be true, or the other way around.
I think the side is true.
Which side? Forward, backwards?
Forward.
Forward is true, right? Forward is true, everybody agrees? Forward is true. Everybody sees that? Yeah? Both contractions are matching covered, so this forward direction is true, that is clear. Right? What about the reverse implication? Is the reverse implication true? Okay, think about it. Yeah, reverse implication is true. Okay. Everybody thinks reverse implication is true. No? No? You have a counter example?
Can't seem to get one.
That is not very convincing. If it is not true, you should get a counter example. Okay, try to construct one if you think it is not true. Try to prove the statement, and where you get stuck, that should tell you how to construct the counter example. If it is false. Hopefully people watching the video are also trying to do this when they watch the video.
I think
Hmm.
take K4 and
K4? Okay. K4.
and just react. Take in that version.
Oh, you want that drawing? Okay, which cut? This cut.
That is not a separating.
This is not a separating cut. Does it satisfy? Can it satisfy this condition? Can it satisfy the right hand side?
For every edge, yeah.
What is the intersection of any perfect matching with this cut? If you take any perfect matching of the graph, then the intersection with this cut is either 2 or it is 0. So the right hand side will never be met. Right hand side will never be met, left hand side is not met, therefore it doesn't work. Right? What you need is one of the two directions should be, one of the two sides should be met, right? So this doesn't work. Four vertices will probably not work. Counter example will need at least 6 vertices. Yeah, because basically what you need is an odd cut. Both sides should have odd number of vertices. Odd cut is just a trivial cut. It will be trivial cut in case of 4 vertices, right? One side will be 1 vertex, other side will be 3 vertices. That is a trivial cut. That is always a separating cut, and it will always meet this condition because of matching covered. So four vertex graphs will not give you counter example.
You need an even cut for
You need an odd cut.
for counter example.
You need an odd cut. Right? For either of these two conditions to be met, the cut has to be odd.
No, for a counter example.
For counter example, one of these conditions has to be met, right?
No, so if you are going with the reverse direction.
I still need the other condition to be, I need either the left hand side or the right hand side to be met. And both of those imply the cut is odd. Right? Separating cut means it is an odd cut. If the intersection is 1 for any perfect matching, then it has to be an odd cut. So, what you need is an odd cut. Your counter example? Try all the 6 vertex graphs you know. I think you will find one. I have not tried one. I think it is not true, but I could be wrong. I don't have a counter example either. Huh. Yeah? Okay, please, on the board. Yeah, if you don't mind being on the video. Alright.
Because I've seen this before.
Oh, okay.
So I started with this graph.
Okay.
Here,
Fine.
this is a barrier,
Okay.
and so this is a tight cut,
Yeah.
of course.
Yeah.
But if I add this edge,
Yes.
this is not a separating cut anymore.
That's right. That's right. This works. Yes. Because it was a tight cut before adding this edge. Before adding this edge, it was true that every perfect matching met this cut in exactly one edge. Therefore, for every edge of the cut, there was a perfect matching containing that edge and only that edge from the cut. So that property will not change if you add this edge. And now once you add this edge, so the right hand side will still be met, But now this is no longer a separating cut, and people can draw the two contractions and figure it out. Thank you. This works. So yeah, this works. The right hand side is true. Please check. To check, remove the edge E and then look at the resulting graph. If you remove the edge E, then this cut C is actually tight in G minus E. Because it is tight, it meets this condition. Every perfect matching will meet the cut in exactly one edge in G minus E. Therefore, for every edge of the cut, because the graph is matching covered, it's a two connected cubic graph, therefore it is matching covered. And now after you add this edge, you can check that the graph is still matching covered. You just have to check that this edge belongs to some perfect matching. And now you can check that this cut, it still satisfies this property. That will not change because you do not destroy perfect matching by adding an edge. But now it is not a separating cut. Forget tight, it's not even separating. The two contractions are K4 and the other contraction is the problem. The other contraction is not matching covered. Right? When you shrink the triangle to single vertex, you get a graph that is not matching covered. Yeah. So this doesn't work, and here is a concrete counterexample. Thank you. So how do we correct it? So it is close to the correct statement, but it is too weak, as we can see from this example. So what change do you want to suggest? Do you want to propose a change, since you are the one who proposed this? You just have to make a small change here, then it becomes correct. So here is one way to think about it. In this example, there is an edge for which this condition is not true. There is an edge in this example. It is actually a unique edge. If I am not mistaken, there is a unique edge in this example for which the right hand side actually fails. Wait, is that correct? Yes, the right hand side fails. I am not looking at an edge in the cut. I am looking at an edge of the graph. So I want this thing to fail. There is one edge in this graph. Now you know which edge it is. Right? For that edge, you cannot find a perfect matching containing that edge and meeting the cut in exactly one edge. Right? That is the edge E. Okay. In fact, there is only one perfect matching containing this edge, if I am not mistaken. I have to match these three vertices, and the only way I can do that is this goes here, this goes here, this goes here. This is what Shalu would call a solitary edge. It's an edge that belongs to a unique perfect matching. Okay. So this perfect matching meets the cut in three edges. Right? So now anybody wants to propose a change? Instead of edges of the cut, you should look at a larger set. You want the two smaller graphs to be matching covered, which means every edge in those smaller graphs has to be matchable. If you want every edge in the smaller graph to be matchable, presumably you need a condition on all edges of the original graph. What this will give you that all edges in the contractions are matchable. All edges of the cut C are matchable in the contractions, which is actually true. If you draw the contractions, you get this graph. This is K33, and then you have this edge. Observe that these edges are actually matchable. In fact, all edges are matchable except this fellow. And the reason this is happening is because here the condition is only for the cut. What you need is all the edges of the graph. Now this is a true statement, and now this is a DIY. Okay? It's not too difficult. Once you have the correct statement, it's actually pretty straightforward. So for every edge of the graph, you want that there is a perfect matching that contains that edge and contains only one edge from the cut. And now these are not equivalent. Now these two things are not equivalent. Because the edge of the cut, the edge of the perfect matching that is in the cut need not be the same as the edge E, because E could be outside the cut. Okay. Now this is a true statement and you can prove it yourself. Okay, questions, concerns? Alright, so what's next? Let's see. Okay, so that's the characterization of separating cuts. Okay. Yeah. And tight cuts here, and observe that every tight cut is a separating cut. But the converse is not true, and for that this is the classic example. Here is a separating cut in the triangular prism that is not tight. Another example is, take the Peterson graph. There are 6 perfect matchings in the Peterson graph. Every perfect matching of the Peterson graph is actually a separating cut. Because it is a very symmetric graph, every perfect matching, you can basically view it as joining two pentagons. If you remove the perfect matching, any perfect matching in the Peterson graph, you will get exactly 2 5 cycles. The 2 contractions will be W5, wheel on 6 vertices. Right? So every separating cut in the Peterson graph is not tight. Or these are the only separating cuts, by the way. The only separating cuts in the Peterson graph are the perfect matchings of the Peterson graph. And they are not tight. Okay? Good. So what's next? Next we will look at 2 important types of tight cuts, and we will see why these are important. Okay, maybe I'll make some space here because I don't need all of this stuff now. Okay. So recall that in a matchable graph or in a matching covered graph, doesn't matter. A barrier is any subset of the vertices such that the number of odd components in G minus B is exactly equal to the cardinality of B. Okay? So now let's consider a barrier. Yeah, so this part we have already kind of discussed, but I want to discuss one more related concept. So if I give you a barrier in a matching covered graph G, and you consider any odd component, well, all the components will be odd because it is a matching covered graph. So let's say J is an odd component of G minus B. Then do you all agree that every perfect matching will use exactly one edge from this cut? Then M intersection partial of J is equal to 1 for every perfect matching M, where partial of J is a shorthand for partial of V of j. Okay, so for a subgraph, I will just write partial of j instead of partial of V of j. Yeah. Do you all agree with this? So therefore, these cuts are tight cuts. In particular, this implies that partial of j is a tight cut. Tight cuts that arise in this manner, they are called barrier cuts. If for a tight cut, I can find a barrier for which this tight cut would become a barrier cut, I will call this a barrier cut. Right? So, this is the definition. Such tight cuts are called barrier cuts. One way to think about this, why is this nice? Think about it this way. What is a tight cut? Tight cut means every perfect matching meets the cut in exactly one edge. So if you want to check that a cut is tight, if you use this definition, good luck. The graph may have exponentially many perfect matchings. Check all the perfect matchings and check that the intersection is 1. Not fun. Barrier cuts, if you just find a barrier and you can see that this is a cut corresponding to an odd component, then you know it is a barrier cut. You don't have to check all perfect matchings. The fact that it is tight just follows from the fact that it is a barrier cut. Therefore it is tight. Okay, so that is nice. If I give you a barrier cut and I give you the corresponding barrier, then you are quickly convinced that it is actually a tight cut. I don't have to show you any perfect matching. Right? I just have to show you the barrier. Yeah? Okay. So that's one way to see why barrier cuts are nice. Okay. There is let's do an example. So standard example is basically what Santosh drew with the without the extra edge. So well, I'll put 3 maybe, why not? Okay, so here is a nice 2 connected cubic graph. There are 4 matching covered. And here you have this barrier. And corresponding to this barrier, you get 3 barrier cuts. Observe that if the component is a single vertex, you will still get a tight cut. It is just a trivial tight cut. What is more interesting is the non-trivial tight cuts. Right? So here is one example. And I also want to define what is called a special barrier cut. Ravindra is quite familiar with this, special barriers. So by special barrier cut, we mean the case where all of these are single vertices and there is only one non-trivial component. Turns out those are actually going to be quite important in the theory. We will actually see examples soon. So let me just give you an example. So, well, okay, sure. Single vertex. But here I will make it non-trivial. So this is a special barrier. So what's a special barrier? Yeah, the term special is not so nice, but well, I think they ran out of terms. So special barrier means it is a barrier B such that G minus B has precisely one non-trivial component. All the other components are K1. Has precisely one non-trivial component. Let's call this non-trivial component J. If J is my only non-trivial component, then the corresponding partial of J is what we will call a special barrier cut. Okay, so this is my special barrier. And what I get for a special barrier is a special barrier cut for that non-trivial component. And for this non-trivial component, the partial of J is called a special barrier cut. Yeah. And these will also play an important role in the theory. Let me ask you a question. For a special barrier cut, one of the two contractions has a nice property. One of the two contractions has a very nice property. A property that is generally very important in matching curved graphs. Most problems become easy for that class of graphs. Easier, if not easy. If I give you a special barrier cut, then one of the two contractions is bipartite. Yeah, one of the two contractions is going to be bipartite, right? And that is one reason why these cuts are actually important. So let me in fact give you a easy DIY. Okay. Okay. So here is proposition 4.3. It's if and only if a tight cut is a special barrier cut if and only if one of the shores is bipartite. One of its shores of course, shore is a set of vertices, so technically I have to say one of its shores induces a bipartite graph. Okay, DIY. One direction is easy. You can all see that if it is a special barrier cut, then one of the shores induces a bipartite subgraph. That is clear. Turns out the converse is also not too difficult.
By one you mean at least one.
Sorry?
By one you mean at least one.
Yes, at least one. Yes, by one here, I mean at least one. Could be both. Thank you. Okay, good. Okay. So one natural question arises once you see this type of tight cuts. The natural question is every tight cut a barrier cut? Right? Am I just fooling you by defining barrier cuts and then I'm going to actually prove that all tight cuts are barrier cuts? So it turns out that is actually not true. It is actually true for bipartite matching curved graphs, which we will either see proofs of in the lectures, or I will just give you exercises, and it's not too difficult to prove. So coming up, in a bipartite matching curved graph, not only every tight cut, but actually every separating cut is a barrier cut. Every separating cut, and thus every tight cut is a barrier cut. In fact, a special barrier cut. Okay?
Induces meaning that contraction.
No. Induce means induce subgraph. So when I say a vertex, a set of vertices, induce is a bipartite subgraph. I mean the graph induced by that set of vertices. This one.
That's four vertices.
Yes. Here I don't mean the contraction. Yeah. Good. Okay. All right. Questions, concerns, anything so far? In fact, I should make it clear that in fact in bipartite matching chord graphs, separating cuts and tight cuts are actually the same thing. This example is non-bipartite for a reason. In bipartite graphs, you cannot give an example of a separating cut that is not tight. So we will actually prove that all of these are the same. Separating cuts are tight cuts, vice versa, and all of them are actually special barrier cuts. That's what we will prove. Or I'll give you exercises because it's actually not difficult, right? But you can already start thinking of it as a TIY. In fact, let me make it concrete, more concrete. Try characterizing separating cuts in bipartite matching chord graphs. Characterize separating cuts in bipartite matching chord graphs. Okay? Good. So, are there any questions or concerns? If not, we can take a short 5-minute break and we will move to the other side. Yeah? Okay, thank you.